Should we sit here first or whatever you do this? Felix can certainly do that, but I will certainly sit here. A grand cinematic for being able to do it.
No, I'll stay here if he's staying here. Do you want me to do an entrance?
No.
Okay.
Should we sit here then and then I'll come? Or should we sit here?
Oh, you know what? I'm gonna do the entrance. I'm gonna do the
You'll
entrance.
do the entrance. Maybe
Okay.
if you stand up here. Okay.
I'll stay through this. We sit here and then once you're...
Sure. Good evening, everyone. My name is Jasmine, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm excited to introduce this event with Felix Flicker, presenting his new book, The Magick of Physics, Uncovering the Fantastical Phenomena in Everyday Life, in conversation with Norman Yao. Thank you so much for joining us this evening. Tonight's event is a part of our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. To learn more about this series and our other upcoming events, you can check out the page harvard.com/science. Before we get started, I'm just going to go over a few housekeeping items. First, please silence your cell phones for the talk. Tonight's event will conclude with some time for your questions. Just raise your hand during the Q&A portion, and one of our event staff will bring you a microphone. If you haven't picked up a copy of The Magick of Physics yet, or if you would like your copy personalized, we will be moving to Cabot Library just across the hallway right after this event for a signing and reception with some snacks. And thank you so much for supporting our series by buying books from Harvard Bookstore. And thank you to our friends at Harvard for all of your help in making events like this possible. Tonight, our speakers are here to discuss Felix Flicker's newest work, The Magick of Physics. This book explores the magical threads that run through our daily lives, drawing on classic sci-fi, fantasy fiction, and everyday phenomena to explain and celebrate the magical properties of the world around us. Felix Flicker is a lecturer at Cardiff University and its School of Physics and Astronomy. His work has been published in both Nature and Science, and he has delivered talks at the Royal Institution. Introducing Felix in depth tonight and moderating tonight is Norman Y. Yao, professor of physics at Harvard. His research lies at the interface between AMO physics, condensed matter, and quantum information science. We're so pleased to host this event here at Harvard Science Center tonight. Please join me in welcoming Professor Yao.
Thank you so much, Jasmine, and it is wonderful to see so many friends and colleagues in the audience, and also to welcome you all over here. Good evening. It's really a tremendous pleasure for me to introduce my personal friend and colleague Felix to you all. Felix has truly a magical way with words, and I think that comes across very nicely in his book. Felix did his undergraduate degree at St. Catherine's College in Oxford, where he read physics and won the well-known Neville Robinson Prize for Best Academic Performance in both his third and fourth years. He then moved on to the Perimeter Institute for Theoretical Physics for a master's degree, and then to Bristol University for a PhD. After Bristol, he crossed the sea and came to Berkeley, California, which is where I first met Felix. And I will share just a little story about my first meeting of Felix. As with all good stories, there was a little bit of a trade involved in the story, and I'll let you decide who won. So Felix and I was a professor at Berkeley, at UC Berkeley at the time, and I was just taking the elevator up to the fifth floor common area where there were lots of theoretical physicists that congregate. And in particular, I was in search of a theoretical physicist who worked on a particular topic related to quantum materials. And I entered the elevator, and at the time there was a long-haired individual who I now know to be Felix, but at the time I'd never met before, and who was in the elevator and had a delicious piece of cake in his hand. as I said, well, what can one do except start a conversation? So it was, all the way from the ground floor to the fifth floor. I said, oh, Felix, what are you working on? I'm a theoretical physicist. Well, me too, kind of. And he said, oh, well, what are you heading up to the fifth floor for? I'm looking for a person who's an expert on this particular nuanced topic called transition metal dichalcogenides. And he said, I did my PhD on transition metal dichalcogenides. And I said, what are you headed to the fifth floor for? He said, to eat my piece of cake. I said, well, I have a solution. I said, let us go to my office together where you can eat your piece of cake and regale me about transition metal dichalcogenides. So indeed, that is how this happy marriage started. Felix came to my office in Berkeley. We went and talked about transition metal dichalcogenides for quite a while, if I remember correctly. And I only know this story sort of in hindsight, but at the time, Felix was quite hungry, he tells me in hindsight, but he felt bad not offering me a piece of cake. So, in his, kindness, he said, well, Norm, would you like to share this piece of cake? As you can see, I never refuse a piece of cake. So I delightfully took this piece of cake, and we had a wonderful conversation about physics. And about 2 weeks after this, Felix came to me and said, well, Norm, I gave you a piece of cake. It turns out my time in Berkeley is slowly running to an end. I need some funding for another year or two of postdoc. And of course, with tremendous pleasure, I said that would be wonderful. And Felix worked with me on a number of really, really fun projects and taught me a tremendous amount of physics during the time that we were together in Berkeley. So it's a little known story, but I hope it gives you a little sense of Felix. After his stint at Berkeley, he moved on to a junior research fellow position at New College in Oxford for 3 years, and has started his lectureship, which is kind of the UK equivalent of sort of a tenured assistant professorship position at Cardiff University. As you will also hear, and hopefully you'll get a chance to chat with Felix after these discussions, he is a man of eclectic tastes, both in food and in life. He has practiced Kung Fu for many years and taught Kung Fu at Berkeley. He was the British national champion of a Chinese style of wrestling known as Shui Jiao, which some of you in the audience might know, so don't get on the wrong side. He's, while he was at Berkeley, he taught sailing, he plays mahjong, he plays bridge. He's really one of the most interesting people that I know. And with that, I'm very, very excited to welcome Felix to the stage, where he can tell you a little bit about the origins of his book. Felix, please.
Hello, everyone. Thank you very much, Norm. That was a brilliant introduction. I was going to start by apologizing for the way I'm dressed, actually. I try to sort of dress up for these kind of talks, and I wear like a tweed suit and that kind of thing. But I've been traveling for about 2 weeks in the US, and I thought with all those flights, they're going to lose it at some point. So I'm just going to go with my normal clothes. And then it turned out that it's just been pointed out to us that we're dressed rather similarly, and I thought, well, you're getting the true theoretical physicist costume here. And we've also realized that we're kind of color coordinated, so he's come in Harvard colors and I've come in Oxford colors, but that was not planned. It came about naturally. Okay, thanks very much, and thanks for coming. So I'd like to tell you a little bit about the book and what it's about and how it came about. So the book is about condensed matter physics, which is my subject and Norm's. Can I see a show of hands who's heard of condensed matter physics in particular? That's fine if you haven't, but so it's maybe half the room. Now, thank you. Now, I usually ask this question, and I expect no one to put their hand up. Now, I kind of knew that wasn't going to happen in Harvard. I thought probably they're all going to know it, and they did. But who's heard, say, of gravitational waves? Slightly, I think, basically everyone, right? And let's pick another one. How about string theory? Who's heard of string theory? Okay, all hands up again. So here's the thing. Condensed matter physics is actually the biggest area in all of physics. So about a third of all physicists identify as condensed matter physicists. And that's more than any of those other subjects, more than string theory, more than astrophysics. But usually if you ask somebody who isn't in Harvard, say, if they've heard of it, they often haven't, but they've usually heard of those other things. So the book came about in wondering why this is. And I think the kind of short answer is that there are really excellent books written about those subjects. Famously, Brian Greene has this book, The Elegant Universe, about string theory, which I loved when I was a teenager. There are many great books about astrophysics, cosmology, these sorts of things. But there were none that really sort of sprung to mind about condensed matter physics, and I think that was essentially the reason why we don't tend to have heard of it. But then there's a kind of deeper question. It begs the question, okay, why is that the case? Why are there no books on this subject? And I've asked people over the years. I've asked scientists, I've asked kind of science popularizers, why is this? And the answers they give, they always seem to fall into essentially two categories. So the first one is, if you think about the subjects which people have always heard of, string theory, astrophysics, and so on, there's kind of something inherently magical about those subjects that doesn't need explaining. There's a sense in which you just look at the stars, and probably people will agree there's something inherently magical about the stars, and I don't need to go into much more detail about what I mean by that, right? Do you kind of vaguely agree with this? Maybe for a scientific audience, I should be a bit more precise about what I mean by magic. I think I mean it in the loose sense. You'd say it's quite magical, and people probably agree. I mean, precisely, I'd say essentially that magic is the ability of the world to inspire. I think that's really what I'm getting at. So it's not, and there are some bits of sort of references to stage conjuring tricks and stuff in the book, but really I mean the ability of the world to inspire. And I think it is inherently inspirational, like looking out at the cosmos and wondering where it all started, where it's all going, that kind of thing. And I think it's probably true also of things like string theory, where you're trying to get at the sort of fundamental building blocks of the universe, right? Or the things that the world's made up of. And again, it's kind of inherently magical. Condensed matter physics is the study of matter. It's the study of the familiar world around us. So like states of matter, solids, liquids, gases, how they change from one state to the other, and how matter comes about from the quantum world. But matter, the stuff around us, I mean, it's very familiar, right? It's our entire existence is matter. We're matter, everything we ever experience is matter. And so magic, this sense of magic, this sense of inspiration seems to be a bit hard to reconcile with that. Because magic needs some kind of incomprehensibility to it. The kind of unimaginably large and the unfathomably small, these things are kind of inherently magical, perhaps because they're a bit unfamiliar. So seeing the magic in the familiar is a bit harder. And the second reason I think there aren't any books written on condensed matter physics is that it's inherently practical. So all of physics is practical, really. Even the most obscure bits of mathematics often end up having uses, but often many years down the line. So when we're looking for gravitational waves, say, or we're doing experiments in CERN to try and detect these elementary particles, the technology that we develop to carry out those searches ends up filtering down into daily life, and we make use of it. But it's often on quite a long time scale. Typically people say sort of 50 years from quite theoretical advances to having an impact in your lives. If you think about it, the most sort of the archetype of an obscure kind of discovery would say something like quantum mechanics. And about 50 years after this absurd world of quantum mechanics started to be understood, it started having practical applications. And these days, you wouldn't have any of your phones or computers, any of that stuff, without understanding the quantum world. So even that has practical applications. But condensed matter physics has practical applications on a much shorter time scale, typically. I wouldn't care to guess how short it is, but it could be a matter of, it could be a few years, maybe say something like 3 years from some theoretical discoveries to really having it be a practical technology. And I think, again, that's kind of at odds with this sense of magic, of wonder that other subjects can conjure, because if somebody wants to tell you about black holes and they write a book on black holes, they're not going to sell them on their practical applications, probably, right? They're going to sell them on why they're excited to work in that subject. They'll say, here's what I think's cool about this, I love this subject, here's what we all think, and their enthusiasm can come across. But if you try to tell someone about condensed matter physics, there's always going to be that tendency to want to sell it on the applications and say, this is great because it's going to make your phone work better. But probably that's not why we're working in condensed matter physics. I can't speak for all condensed matter physicists, but that's not what motivates me to go and work on these problems. So I think those are the two essential reasons why people tend not to have heard of the subject. It's practical and it's familiar, and those two things seem to be at odds with this sense of magic that's present in other physical subjects. So that's what led me to the idea for the book. And So maybe I'll tell the story about how I kind of started to write it, because I tried a few times over the years. I thought I'll sit down, on a Sunday when I've got nothing else to do, I'll try and write a popular science book that talks about this subject. And I would come back to it each week, and it was very inconsistent. It would be, one week I'd sit down and write something, and it would be really technical. It would have equations in there. I was like, they've got to see Maxwell's equations. I'll just put those in there. I'll do some algebra there. And then the next week I'd sit down to write it, and it would be coming out like far too simplified. I wasn't really explaining anything. Totally different. It was very inconsistent. And then at some point, I guess about 4 years ago, I had the idea to instead start with a fictional passage. So there's fiction in the book. And I started with this fictional passage of this wizard called Varian, this female wizard on some kind of adventure, which you're not sure where she's come from, where she's going, but she's in some cavern, and she takes from her pocket a crystal, and through some magical means, she causes this crystal to light up, okay? And I thought, okay, we can agree that bit is magic. If some wizard's pulled a crystal out of their pocket and done something to make it light up, that sounds pretty magical in the traditional sense. Do you agree? Getting some nods, thank you. So then, here's the thing, I open with this fictional passage and then switch to non-fiction and point out that we actually perform this magical act all the time. We're probably doing it right now. I should think we are, because typically, maybe not with these ones, but lighting these days is typically LED lighting, light-emitting diodes. And LEDs are nothing but crystals. So we have crystals, and we do cause them to light up all the time. We just pass an electric current through them. So you could say, okay, so maybe it wasn't magic when the person did it in the story. Maybe it's not magical to light up crystals. But the thing I wanted to try and convince people of with the book was you should look at it the other way around. You should say, no, it was right to say it was magical when it was presented in this kind of fictional context, but then you must also agree that it's magical whenever you turn on a light. It's just practical and familiar, but it doesn't stop it being magical. So I think the subject is inherently magical, and I was led to this idea that, well, it's a particular kind of magic, maybe a kind of subtle magic, but it's kind of inherently the sort of magic a wizard does in whatever your favorite story with a wizard in is. And I should say that I want to include everyone in the set of wizards. It's not intended to refer to a sort of old white man with a long beard, although obviously I am heading towards that stereotype myself, but we can't get away from that. But so if you think of your favorite wizards, like say Harry or Hermione in Hogwarts, or Morgan Le Fay or Merlin in Arthurian legend, whoever, think of your favorite ones. They don't do magic that kind of alters the cosmos itself, right? And they don't do magic that changes the fundamental laws of reality, typically. What they tend to do is bits of practical, hands-on magic that helps out the other characters, okay? And so I thought that's essentially what condensed matter physics does. It's that kind of magic, the practical hands-on magic that's actually helpful to people. So that's the idea of the book, that the world around us, it is familiar, and we put it to practical use, but that isn't actually at odds with magic. It's just a kind of slightly more subtle sense of magic. And we can return to kind of reappraising the world around us and see it in a more magical way. And that's what condensed matter physicists, such as myself and Norm and many others, do. So that's the idea of the book. I think I'll probably just leave my introduction there. I think I've covered the main bits.
Okay, excellent. Fantastic. So Felix asked to sit on the left. I don't know why, but we're going to switch.
I had this image in my head that I should be on the left. I don't know why.
So as Jasmine mentioned, I'll start kind of, talking to Felix a little bit, probing a little bit about a book, about, his general perspective. I see that there are many budding young scientists in the field, so I'll try to start at 10,000 feet, but at some point I'll totally turn it over to you. So as you hear Felix answer questions, feel free to jot down your own questions, and at some point we'll sort of turn the conversation over to a Q&A, and I'll continue to help guide the discussion, but it really should be a conversation between all of you and Felix. I have known Felix and had many conversations with him. Okay, so I wanted to start kind of very broad. This is something that you do mention, I think, already in chapter 1 in the book. Maybe 100 years ago, I would say, there was just the notion of a physicist or a chemist, and there was a distinction between a physicist or a biologist. But these days, in more modern physics, it seems like there's the distinction that you allude to between the difference between an experimental physicist and a theoretical physicist and other types of physicists. So in your life as a theoretical physicist, what do you feel like defines the work of a theoretical physicist? What does it mean to be a theorist in the language of physics?
Okay, great question. And okay, so yeah, as Norm says, I think there are probably three kinds of physicists. Would you agree with that classification?
Yeah, probably.
That's how you classify it. So there are experimental physicists who do the actual work, actually go out and find what's going on. Then there are theoretical physicists, and I'm a theoretical physicist. And we we can either try to explain the experiment. Sometimes experimentalists come to theorists and say, here are my data, can you explain them? And sometimes theorists will come up with a theory and go to an experimentalist and say, can you find a way to realize this? The third type, I'd say, especially these days, is a numerical physicist or a numericist. And perhaps, so they would say create computer simulations. They'll use heavier numerics to try and get at problems. I think perhaps if I draw the distinction between the theorist and the numericist, that's probably a good way to think about it. Because I suppose actually, so I had a conversation with my. Sorry, maybe this is a bit close to my mouth. There we go. I had a conversation with my PhD supervisor when I was doing a PhD years ago, where we were trying to. Actually, it was the particular thing I heard you mentioning at the start there, was the transition metal dichalcogenides, calculating those band structures, and. I said, well, we've got sort of 2 free parameters in our model. If we make it like, I think it was about 36, we'll get this to fit much better. That'll be really good. And he had to explain to me, yeah, but that's not what you're trying to do. You're not trying to make the most accurate reproduction of reality. You're trying to boil it down to its essence, find like the key thing that captures what's going on in the phenomenon. And I think that was kind of the distinction, because I'm a theoretical physicist rather than a numerical physicist. A numericist might work closer to trying to simulate something more accurately, whereas a theorist will go for a less accurate model, but one that still does the essential thing you want it to do, so then you can say, well, these are the things that really matter. Now, it won't be perfect, but it'll get the essence of it. I think so that was a good way for him to explain it to me, and I understood why we didn't want a 36 free parameter fit. But sometimes those things can be useful. I should say, actually, Norm here is unique from people I know in really being all three physicists. And almost everyone is one or the other. They're either a theorist, a numericist, or an experimentalist. And Norm really is, he's actually, he's a top experimentalist, and a top theorist, and a top numericist, all at the same time. He really is. It's uncanny. I don't know anyone else who does all three. Actually, we were having a chat earlier, and I asked him how he thinks about things, because I think we do think that the three types tend to think of things in different ways, right? Yeah. So, and which one would you go? Who do you feel like at heart?
Probably, I should say with true clarity, all of the glamour goes to my students. I think both those that I've taught and those that I'm continuing to teach. I think I would not be where I am without them. But I think I probably think about things similar to you. I probably as a theorist more than anything else.
Okay, so we're trying to sort of boil things down to their essence.
Yeah, I think that's right. Often I'm sort of guided by that flavor of a question. That was a brilliant answer. Maybe diving down a little bit deeper along sort of the same thread. So when you were introducing, you sort of explained to us, this notion of practicality and familiarity in terms of the things that we see around us as kind of, one of the essential reasons why condensed matter physics maybe is not as magical as it could be. So maybe as an even broader introduction, so we have this distinction that Felix was mentioning between theorists, experimentalists, and numericists. But I think in modern physics, even as a theorist, there are even more subtle distinctions. In graduate school, people are atomic physicists, or optical physicists, or biophysicists, or high energy physicists, or most common, condensed matter physicists. So maybe you could sort of zoom in and tell us a little bit, in the problem space and the types of questions that people are asking, what sets condensed matter physics different from the other types of physics and subfields that people explore?
Okay. All right. Well, so I suppose I should start by saying there's obviously lots of overlap, as you well know, because you work with a lot of atomic, molecular, and optical physics. There's much overlap, but I think there are some things that are essentially condensed matter that don't appear in other places. The simplest way to put it probably is that if you think of particle physics, string theory, when you're looking at elementary particles in CERN, you're typically sort of working in the limit of essentially one particle, right? You're trying to find a single thing. Like a particle would be something like an electron or a proton. You're probably not looking for those in CERN, but you might try and find some new particles that are like that. And there might be a few, but typically you're in the limit of one. Condensed matter physics kind of works in the opposite limit, right? So to a first approximation, you might actually say there's an infinite number of particles. Now, infinity sounds harder than one, but actually I wouldn't say it's not necessarily. Things become a lot easier when you say there's an infinite number rather than a large finite number, I think. So maybe a simple way to say it, well, if infinity is simple, maybe it's not, but maybe to a first approximation, we tend to be thinking of huge numbers of particles at least, and possibly to a first approximation infinity, as opposed to particle physics, which would be more in the limit of one. Both are difficult limits. In the middle it gets very tricky, and I think that's where you get onto sort of perhaps some more atomic and molecular physics when we start to go to a few. Does that sound like a reasonable?
Yeah, let me try to delve a little bit deeper. I'm not sure I even understood that. So let's try to understand that. Let's try to explore together. So I think this is, maybe another concept that features prominently in the book. I mean, all of us, sitting here are familiar with the idea of a particle, as you just said. There's particles that, Professor Franklin is trying to discover at the Large Hadron Collider, or there's particles that we're more familiar with. In an atom, we learn in grade school that they're made up of electrons, protons, neutrons. We think of those as particles that make up an atom. At least that's very natural verbiage that one would use even in grade school. But one notion that features super strongly in the book is this notion of a quasi-particle. And you sort of emphasize that this idea of a quasi-particle is kind of the backbone of condensed matter, or what separates it from, the distinguishing concept that separates it from other subfields of physics. What is a quasi-particle?
Yeah, good. All right, so I think that is, I thought about what's something that doesn't really appear in the overlaps with other subjects. And I think quasi-particles are exactly that. I tend to say quasi, by the way. Some people say quasi. I don't know what the correct pronunciation is. There's all sorts of pronunciations. I'll say quasi.
Accept you as a Brit.
Well, I think Roger Penrose says quasi, and I'm not going to argue with him about it. Well, I am, because I'm going to say quasi, but so quasi-particles. It's a great question. So, yeah, particles you might look for in CERN would be what we'd call elementary particles. Things, let's say this is going to be a definition I've come up with. I had to think of something that can explain it. Let's say there's something that can exist by themselves in the vacuum of space that can't be reduced to other things with that property. Does that sound kind of reasonable? So then you could say an electron has that property. An electron can exist by itself. And it's not, we don't think it's made up of anything smaller. An atom can exist by itself in space, like a hydrogen atom, but an atom can be broken up into other things. It can be made up of protons and electrons. So that then wouldn't be an elementary particle like that. A quasi-particle is something really that can only come about in matter, when you have lots of other particles there. You're not going to disagree at that point? Okay, good. In some cases, imagine you have some lump of matter. Here's a lump of matter right here. Okay. We might imagine something like a metal or something, but I've got a lump of book here. Now you might have an electron, an elementary particle that can travel by itself through space, but then it can enter material, right? It can enter this matter. And when it does, what's it going to do? Well, it's going to interact with all the stuff that's already there, right? There's a load of atoms in this book, and those are made up of electrons and protons. Those are electrically charged. This electron can interact with those, and it can pull them towards it, say, and it can cause these vibrations in the matter. Now, the weird thing is, you might naturally say, well, it's just like an electron moving through some other stuff. But the way we think of it, and I think the more accurate way to think of it, is that you can't really break things down into those separate pieces so much, right? It's really that the electron interacting with stuff, you've got this kind of collective behavior. And I think that's kind of gets to the heart of condensed matter physics, when things start behaving collectively. The phrase I use in the book a lot is this Aristotelian one, that the sum is more, the whole is more than the sum of the parts. There are many cases instances where this is the case. And quasi-particles kind of capture this idea quite clearly, I think. So if I give maybe my favorite example, it's my favorite example. Some people disagree that it's a quasi-particle on sort of technicality. So a phonon, would you call a phonon a quasi-particle?
Yeah, okay.
Some people prefer it, to call it like a collective excitation or something, but let's call it a quasi-particle. I think it's a legitimately cool one. So an elementary particle you might, you've probably heard of is a photon. Have we all heard of photons? So this would be a particle of light, right? In the quantum description of light, a classical description would say light is a wave, but you could say I've got some beam of light, or I've got lots of light coming down here. What's the quantum description? What's it doing on the smallest scales? And you can describe it as being a kind of flow of individual particles of light, which we call a photon. Now those fit the definition I gave earlier of an elementary particle, because a photon can exist by itself in the vacuum of space, and it can't be reduced to anything else with that property. We know it can travel through space because we can see the sun, for example. Now, you can't have a particle of sound, right? Because by my definition, sound can't travel through space. Sound can't go through a vacuum, right? So if you accepted my definition earlier, then you'd have to say there is no such thing as a particle of sound. But sound can travel through matter. I mean, you're hearing me right now. If I shout into the book, the sound would travel through the book and come out the other side. So it turns out that within matter, especially within crystals, which tend to be something we like to focus on in condensed matter physics, when sound travels through a crystal, you can actually describe it as being carried by particles. And we call those particles phonons rather than photons. And they're like particles of sound. So those are my favorite examples of quasi-particles, because you could say, there's not really anything there. It's just a kind of, it's really atoms vibrating, right? That's how the sound is traveling through the matter. But in a true mathematical sense, the maths we use to describe that behavior really does describe it as individual particles. And actually, it's the same maths we use to describe individual particles in particle physics. So we use this quantum field theory, it's called. It doesn't matter about the details of what that means, but that's the standard model of particle physics. We can describe photons with quantum field theory, but we can also describe phonons with it, and it's the same maths. It really is the same stuff. So it just says that you can think of sound traveling through matter as being carried by particles. But you can see they just couldn't exist outside of matter. So that would be an example I would give of a quasi-particle, something which comes about as the whole which is more than the sum of the parts. You could say it's individual atoms vibrating, but that would be to miss something essential in the description.
It's super helpful, yeah, okay. So let me try to reinterpret that a little bit and ask just a little bit further about that. So I think what you're saying is that, in principle, if all of us were sitting here in vacuum, wouldn't be very comfortable, but if all of us were sitting here in vacuum, I think you're saying that if I take a flashlight and I shine it at the audience, they'll see it, because there are photons, individual particles of light, that are particles and that can travel through vacuum, which is not made of anything, does not have matter there, but the light can travel because there is an elementary particle there. But what you're saying is that if we were trying to speak to the audience and we were in vacuum, they wouldn't hear anything.
That's right.
Because there's no medium, there's no collective medium to sort of be able to carry the sound to that. Is that sort of what the idea is there?
Yeah, exactly. But you can do it when you're in some medium, which we
Right.
are now because we're surrounded by air.
Right, exactly. So it's the air that sort of it's this, I guess, excitation. The word you used was excitation, sort of in the air. What does excitation mean? I mean, it's easy to think about excitation in a more standard word, but what do you mean when you say it's an excitation that's traveling through that you think of as a particle?
I'm glad you caught me on that. I didn't notice I'd said excitation. But it fits the intuition, I think, right? When you say, when we think of excitation normally, it's getting all excited and being a bit more lively and energetic, right? So I would say that. An excitation would be when you've got, it's a description of energy traveling through a system, say. I think it would have to travel.
And so if we, maybe just to drill on this even a little bit further, so if there are these elementary particles that we think about, and I can also think about something traveling through a medium, what is the use, why is it powerful to think about these things that are traveling through a medium as quasi-particles? Why is that description powerful, and why does condensed matter use it?
That's a great question. Off the top of my head, I'd say, remember I started by trying to describe condensed matter physics as the study of stuff that, to a first approximation, has an infinite number of particles in it. Now, how are you going to keep track of all those? Well, I guess one way to look at it is that the natural way is to not try and keep track of infinity things, but this quasi-particle description can say, it's a way of describing it such that you're really describing like one thing again. So it's getting back to exactly the same thing you would have studied it in particle physics. You're working now in the limit of one thing, but that one thing is like an excitation of loads of other stuff. I suppose this is going to be a bit of an inaccurate analogy, but you could think of having like a rope, say, and kind of whipping one end of the rope and sending like a sort of shockwave down it. Now there's a description of that in terms of a huge number of atoms, right? And you could try and model it as saying, okay, this atom's coupled to this atom's coupled to this atom, and you keep saying that about 10 to the power 24 times or something to get a rope. Or you can say, well, look, when I've whipped it, it's much more natural to describe it as, look, there's one blob moving down the rope. And so I'd say that's the essence of what you're doing with this quasi-particle description.
I totally agree. I totally agree. I think that simplicity of sort of being able, and gets back to the essence of what you mentioned in terms of trying to describe phenomenon in nature in sort of the simplest bare bones toy model to get the essence of the physics right without necessarily needing to keep track of kind of all of the individual degrees of freedom, all of the individual particles that make up, for example, the piece of rope. Mm-hmm. So let me try to move on to a slightly different topic, one that features in work that Felix and I have done together, and one that also features quite prominently in the book, and that's the idea of noise. So I think all of us in the audience are familiar with the idea of noise, and usually we think about that not necessarily being in the most positive of contexts. Oftentimes noise is followed in our modern life with the word pollution. Noise pollution, there's too much noise from this, there's too much noise from that. But it turns out in the book, you sort of give an opposite spin on the idea of noise as a very powerful way to understand the condensed matter physics of what's going on. So how is it that noise can be sort of useful, and what is it about noise that becomes useful to understand phenomena?
Wow, okay. I feel like I'm in an interview now because you're the expert on noise. Noam is one of the experts on noise. He does some fantastic experiments on it. And we also have Amir Yacobi here as well in Harvard, right?
Yep.
Also another expert on noise.
Wonderful, yeah.
So I'm in the home of noise studies. I love noise these days. I've got right into it. I can just tell them about our thing. Sure, go
for it.
I won't talk generally about noise. There's a lot of stuff is known about it. As Norm says, you tend to think of noise and signal, right? And noise is the bit you don't want, and signal is the bit you want. We were involved in a study where we were looking for a particular phenomenon. So it's a type of magnet. Now, there are many types of magnet, it turns out. You tend to think of a magnet as we'd think of a ferromagnet typically when you think of a magnet, right? Which is something that is just magnetic in and of itself. But you also have other types of magnet, like something called a paramagnet, which is not magnetic by itself, but when you bring a magnet to it, it becomes magnetic. So there are actually a few other types, and we were looking at a very exotic type of magnet called a spin ice. They're very a really unique and strange kind of magnet. And we were looking for signatures in these spin ices of a form of, again, people debate whether it's technically a quasi-particle, but you can reasonably call it one, a collective excitation, let's say, which resembles a magnetic monopole. So a magnetic monopole would be like the north pole of a magnet without the south. Now, I guess everyone here knows that's impossible, right? Do we agree? If you take a magnet and you try and chop it in half, you don't get a north pole and a south pole, you get two small magnets. It's exactly like what doesn't happen with a worm, I think, doesn't it? But naughty children think it probably does, but I don't think it happens there. But with magnets, you chop it in half and then you get two smaller magnets. You can't get a north pole without a south. Now, people had theorized that these very strange types of magnet behave as if they have kind of individual north and south poles floating around inside them. They can't come out of the material, but inside the material there's a real sense in which you can think of it like that. And so it's a beautiful theory. It's probably one of my favorite bits of theoretical physics. But the trying to prove that that's the case is the tricky thing, right? There's lots of evidence, but there's not really this sort of smoking gun evidence of these things. So what we'd done was, actually, Norm, after the bit he told you about, where he asked me about these transition metal like quadranites, I kind of asked what it is he was doing there, what are you up to in Berkeley? And I think if the story is right, he'd I think a lot of places wanted to get you, right, to hire you back at the time. And I think Berkeley had kind of sealed the deal by saying, well, you're a theorist, but have an experimental lab thrown in with the mix. Is that how that went? Or?
A reasonable rendition.
Which, this is not normal. Normally they don't say to theorists, so, we really want you, we'll give you a whole lab. You just go and do some experiments and that. So he was building this NV magnetometer, that's right, isn't it? So an incredibly sensitive detector of magnetic fields, which is kind of unparalleled in what it tries to do. It's really taking something the size of a single atom, and you can measure the magnetic field that's being felt at the size of that thing. And he asked if I had any use for this thing. He said, what can I use it for? I've been building this machine, I've got some great ideas for it, but what would you put it to use for? And I said, well, you could probably try and detect a single magnetic monopole inside these spin ices, the thing that we've been wanting to do for 25 years at this point, maybe 20 years. And so we got chatting about it and tried to work out the details. It seemed like it might, it wasn't immediately a silly idea, which is, you usually spend a day or two trying to work out if it's a silly idea, don't you? And we got past that stage. But then we thought, okay, how do we do this in detail? What do we actually go and look for in an experiment? And I think that's when we started speaking to Amir here. And then we spoke to Steve Blundell in Oxford and his PhD student, Fran Kirschner, who ended up doing computer simulations, like numerical simulations. And I think Fran's simulations essentially said, well, under realistic conditions, there would be so many of these monopoles, basically. The conditions at which the experiment can actually operate, of temperature, basically, meant that you would have loads of these things. So it's kind of like we'd sort of worked out what the sound of a single raindrop would be like. It's like we predicted, someone else had predicted rain, and we thought we'd come up with a way to test this theory of rain. And we're like, I think a raindrop will sound like this. And then you go outside and try and listen to it, and it's raining, and it sounds like because you can't listen to a single drop, right? You have to listen to loads of them at the same time. So that's noise, right? You don't hear the signal of the single drop. You hear this noise. But in Fran's simulations, we saw signatures that there was some structure to this noise. And in essence, these paramagnets, the quite common one, the one that when you bring a magnet close to it and it becomes magnetic, it turns out that if you measure the magnetic field around one of these things, you can calculate analytically, as a theorist, exactly what the noise will sound like. And it's what's called red noise. Kind of an analogy to red light. So you've probably heard of white noise. Has everyone heard of white noise? It kind of sounds like pretty horrible to listen to. So white noise is named in analogy to white light, because if you take all different frequencies of light, all different colors, and mix them together, you get white light, right? Now, if you take out some of the shorter frequencies, or either you add in more of the longer wavelengths, the redder colors, then you can still have like a mix, but it'll be more of a pink mix in that case, right? And so red noise follows that analogy. It still kind of sounds like shh, but it's got more of the deeper tones. It sounds more like shh instead. So the paramagnets should sound like shh, and Fran's predictions of a simulation seem to suggest that the spin ice shouldn't sound like shh, it should sound like shh. Now, it wasn't white, that was between white and red. It's what's called pink noise, right, because it's somewhere between red and white. And this is a mathematically precise way to put this, but the easier to understand way is shh. So we made these predictions, and then, and I should say that the noise, the crystal is not literally making a noise, it's that you measure the magnetic field, and if you were to plot that as a function of time, it's sort of oscillating up and down, and it's got a mix of all different frequencies of oscillation, much like the noise of ch does with the mix of sounds. So we were involved in that, and then Fran Kirschner, who did the work on that, she gave a talk about it at a conference, and in the audience was an excellent experimental physicist who's now in Oxford, who's also based in Cornell and Cork in Ireland, Seamus Davis, and he said. Well, actually, I think, so basically she gave the talk. 6 days later, I think, he got in touch and said, my student, Ritika, has measured it. She's built a device, she's measured it, and she's found that signal that you said. Now, this is not a normal timescale, right? Usually, a theorist might say something, probably they would be believed for a while, maybe people make the theory a bit more plausible, 10 years later the experiment starts to be funded, this sort of thing. So 6 days is not a normal turnaround for this type of thing, but that's, that's what they did. And they heard it. So they heard this not and not.
Yeah.
Sound good?
Yeah, sounds, yeah, exactly, perfect. I think I got it. But let me try to unpack it a little bit and see if I get it right. I mean, so I guess in some sense, we think about signals in nature as very smooth objects. You might imagine seeing a signal and seeing that, you're trying to look at an oscillation that looks like a sine wave, for example. And what Felix is saying is that, most of the time in nature, there are fluctuations. There's noise on top of the signal. If any of you have thought about signal processing, that's very natural. In some sense, the sound of that noise, I think beautifully explained by Felix, can be different depending on different types of situations. And it turns out sometimes it's very, very hard to measure a signal. For example, imagine really that you see a flat line. It's not a sine wave, but you see a flat line. And you can't interpret anything from that flat line as a function of time, but maybe what you can see are that there are wiggles around that flat line. But it might be that the nature of those wiggles, if one looks really carefully and looks at the frequency of the wiggles, or the spectrum, or how much amplitude there is at different frequencies in those wiggles, you can still learn something. And that's, I think, one of the beautiful things that's explained in Felix's book, this idea that, oftentimes we're super focused on noise, a signal, but sometimes if you look in the noise, you can actually learn things that are very deep, that may be more difficult to analyze and see if the signal isn't there. Okay, so I'm going to ask one more question, and I'll turn it over to the audience. I think we've now Felix has given you a sound bite, so we'll ask maybe a little bit of an existential question, then I'll turn it over to the audience for a little while, and maybe we'll come back to a conversation. So one of the central things in the book is this idea of applications, and the idea that condensed matter physics, really is at some level focused on being able to be useful, being able to help mankind, being able to move towards new applications, new technologies. And I was wondering a very broad question. There are many sides to this answer, and I'm very interested in hearing your thoughts on this. So as, society and humanity becomes more and more integrated with the notions of a technology, I mean, all of you have, I'm sure, seen the magic, the mystery, the scariness of ChatGPT. As we become more integrated in that, in your deep feeling, is technology maybe based on condensed matter physics? Is it the answer to humanity's questions or problems in some deep sense, or is it not? Or is it create more problems in some other deep sense?
Okay, I suppose it depends which problems. Does that sound about right? I think that there's a tendency to think that technology will get us out of certain situations. I think the obvious example would be like climate change, say. There's a sort of hope that some of the technologies I discuss in the book, things like superconductors that can conduct electricity without loss, those could certainly enable the adoption of more renewable energy. For example, you could, the classic example is like covering the Sahara in solar panels and sending the electricity out to anywhere that needs it. Now, we can't do that at the moment because you lose some of the energy as you try to transmit it, and you'd always end up losing so much it wouldn't be worth it. Now, if you could make a material that can conduct perfectly without loss, then yes, you could do that in principle. You could send the electricity as far as you like, and you'll never lose any. And superconductors do this. They already exist. The problem is they only seem to work at very low temperatures. But one of the pressing questions in condensed matter physics is how to get that temperature at which they operate up to room temperature. And if you could do that, then yeah, it would be a major step forwards in the adoption of renewable energy. But I don't think it would solve the problems with climate change, because if tomorrow energy were twice as cheap, then we'd just use twice as much of it, wouldn't we? Probably. So I think it's going to take more than just technology, but I think technology is like a key step in that process. With other things, I don't know, ChatGPT is a good example. Some people are worried about their jobs with things like AI. I think theoretical physicists generally aren't too worried about their jobs, are we? I'm usually quite up for it. I think For AI to replace a theoretical physicist, it would really not only have to understand everything, but also explain everything to everyone so that everyone understood. That's a pretty big task. And if it does do that, then I'm happy to retire, I think. But it depends on your technology, probably. What do you think?
Yeah, no, I think I'm certainly generally in agreement. I think there are interesting things where technology can move us in the right direction, but oftentimes I think there are challenges that are deeper than sort of what technology can solve. Okay, maybe on that note, let me turn it over to you guys. So wait, do not ask your questions yet. We have a helper who will bring a microphone to you. But please, it's be wonderful, for all of us to engage together with Felix. So raise your hand if you have a question. All right, let's start up top.
I have a question, actually. Can I steal some of your water?
Yes, of course.
Thank
Yeah,
you.
please. There's more.
Hello.
Yeah. I think we can't hear. Is the microphone?
Hello? Is it working?
Yeah,
Hey.
I think we're okay.
Okay, so I'm not a physicist. I come to this talk more interested in the magic part.
Oh, great.
I didn't really read the description, but I'm glad I came. There's a question. So I guess I'm hearing you speak about this, and I'm trying to use language and concepts that I understand as somebody who is spiritual. And I'm hearing you kind of talk about condensed matter physics as if it's something that arises out of relationships, perhaps. Or a phenomenon you can observe when some things are in relationship with each other. And as somebody who's spiritual, there's this idea of like there's no one self. You kind of change according to the people you come in contact with. It's not essentialist in the same way that I think you're talking about condensed matter physics. There's no essential matter there. So I'm wondering, the question is, when you're studying a phenomenon of interaction and you kind of have this interaction with other matter, does that still speak to the same paramatter? Does that make sense?
I think I understand something from the question, yes. I think I've got it, but
Okay.
tell me if I get it wrong.
Sure.
Thank you, I like it.
Thanks.
Okay, so first I'd like to say I'm really glad you've read the book, or you're planning to read the book at least, because with this whole Magick angle, I did really hope to engage people that might not typically have read popular science, say, and I was trying to reach a new audience. And ideally, the people I really wanted to reach are people who might be convinced to study the subject further as a result, rather than just sort of writing for people who always read popular science and they're like, oh, there's another little thing to know about. I wanted to engage new people, so I hope I hope you enjoyed that aspect of it. I definitely think there's an analogy to draw there with what you're saying. Condensed matter physics, like one of the things about it is that, exactly as you say, you can't really think of things in isolation. It is, again, this whole being more than the sum of the parts. You can't really, it's not incompatible with this idea of reductionism. I'd say it's really, it is compatible with that, but we're looking for things that you would lose something in the description if you try to treat things as individual. It's really like the collective behavior of stuff that's important. Like the quasi-particles I talked about earlier are a good example of that. You could say these phonons, these particles of sound, there's nothing really there. It's just a load of individual atoms just moving, and if you look at the collective movement, you think there's something there. But that's really not correct at all. It's really something there, which is a collective behavior. That's what the maths is telling us. In exactly the same way that it tells us that an individual electron can exist. It's the same mathematics. I do, so something I hope it's kind of corresponding to a shift in people's kind of attitude towards science. There's a kind of like, the traditional, the very sort of outdated view is that a scientist is like this person by themselves and they're totally independent of nature and they go around sort of, I bend nature to my will, I make it do stuff, And I think I think we probably agree that's quite an outdated view of how it works. Condensed matter physics is more like you can't really isolate things in that way. It's a matter of trying to deal with things where the collective behavior is the most important bit. So I hope that kind of corresponds to a general trend in scientific thinking that you can't really think of the scientist as separate from the environment. Yeah, okay, I'm not really talking explicitly in a spiritual sense, but the sorts of problems we're thinking about now are the ones where you can't isolate things in those ways. That was kind of, perhaps it was always the plan, you know, the simplest thing is where you can isolate stuff, but the real world isn't like that. We need to start thinking about stuff collectively. Does that kind of address what you're asking?
Yeah, I guess, sorry to belabor the point, but I guess, you know, you use the example of sound. So what if you're, you know, trying to speak through water, and it's a different medium, it's a different reaction, different matter interacting with each other. Can you still call that sound? Does that make sense?
Yeah, you'd call it sound. Whether you'd call it phonons is, there's a bit I kind of glossed over there, which is that strictly you'd only say you have these phonons, the particles of sound in a crystal, really. Whereas water, strictly, you wouldn't really describe it in that way, I'd say. But yeah, I'd say that's certainly something you're interested in. Thank you very much for the question.
Thanks. Other questions? All right, so now switch to the front.
Okay. And thank you, Felix. It's a very good talk this night. So,
Thank you.
as you know, this week that in a March meeting, some scientists claim that they have observed the superconductivity in the ambition condition.
Yeah.
So, I'm curious about what do you think about? I mean, the importance of the superconductivity in the ambition condition. I mean, you can answer this from the Felix theory side or the importance for the real life, the world.
Okay, thank you for the question. Yeah, so the question is, the March meeting is like the biggest meeting of condensed matter physicists in the world. It's just taken place in Las Vegas for the last week, which is...
It doesn't always take place in Las Vegas.
No, it's,
just to put it out there.
in fact, actually, I was just told that there's a biography of Philip Warner Anderson, who's like one of the founders of condensed matter physics, and it says in this that the March meeting took place there before, and physicists got banned from Las Vegas as a result.
That's right. Do you want to tell the story, Felix, for why this is the case?
Well, what I heard was it's not the exciting reason you might think that they were going around doing a sort of fear and loathing style destruction trail. Apparently, it's just because they didn't want to spend any money, and this wasn't.
That's right. So it turns out, as far as I know, a tiny digression. It turns out, as far as I know of this story, and it's sort of now become more lore than story, I guess. I think many years ago, Vegas hosts lots of conferences, not just physicists, but oftentimes Vegas tries to attract, big conferences that bring a ton of people to the city. And the idea is that, oftentimes, the city as a whole will, do well from the economic perspective. And so the city will comp a lot of stuff. They'll say, okay, you can use our convention center for free, essentially, or you can do this for free, and we'll give you these, economic advantages if you host your massive conference here. And it turns out this was the case, I think, tens of years ago. The biggest physics conference, March meeting, was held in Vegas, and the physicists flocked there, and I think there was, essentially lots of economic advantages given to the American Physical Society, which hosts this conference. And then, physicists didn't spend a buck there. It was, just, the craps tables, the poker tables were just empty, barren, and then afterwards Vegas said, never again.
They've evidently changed their mind because we were back there.
Well, as it turns out, memory, decays quickly.
Sorry, I should answer the question.
Yeah, sorry, well. Of course. I'm sorry. So yeah, exactly.
So I was there. Probably the most exciting thing that happened was there was a talk with a group claiming they've established superconductivity under ambient conditions. So I think this is room temperature and not too high a pressure. Pretty high, but not as crazy high as it used to be. Now, I was one of the members of the huge crowd that was being held back by security at the door. It was, we got there in sort of 10, 15 minutes early, and the room was already full, and yeah, there was sort of security telling us to step back, and we weren't allowed closer to it. I think there's videos of this online, because it's quite a controversial claim, and I think everyone wanted to see what was going to happen. Now, I suppose the question was actually, what would be the practical effect of this? Is that the...
Yeah, I think you can say what's the importance of, if it's true, so what's the importance for the Felix theory breakthrough, or what's the importance for the practice in the world? Yeah.
Yeah, well, I mean, it's monumental for everyone if it's true. I mean, for humanity, it's monumental if it's true, because as I said, you can now pass electricity from one place to another without losing any at all along the way. So you can generate it like renewably and locally, taking advantage of whatever you've got wherever you are. Sun or less sun in England, but I don't know. We'll have to work out something about rain. I don't know. But then you can send it as far as you like, and you won't lose any along the way. I should say this isn't like just a sort of crazy idea. There's actually various places that already use superconductors to conduct electricity and use it, to power large regions. So I think it's Essen in Germany already has superconductivity for power lines. And so they bury them underground, and then they have to cool them down with liquid nitrogen to make them work. But it's actually already viable. But what will happen is that a lot of energy is being used to do that cooling and so on, and that energy won't be needed anymore if it works. Norm, I think Norm's one of the people connected to this field, I suppose. Do you have any thoughts on it?
Okay. So I mean, certainly, I mean, I've been excited many times in my life, but the announcement that there is near ambient superconductivity, kept me awake the last couple of nights. I mean, that would be, a tremendous advance, unlike any I've seen in my lifetime. But maybe just to give a little bit of a physics background for this idea, just for 1 second, I think some folks might be interested. As is gorgeously explained in Felix's book, about superconductors, the idea is that, some materials, and the most easy ones to understand are elements. So you might say, well, okay, we look at copper. Copper conducts electricity, but it does so with some amount of resistance and some amount of loss. Other metals like gold and silver also conduct electricity, but there are some elements, niobium, for example, where if you cool them down really, really, really cold, think much, much colder than your fridge, it turns out that at some point they suddenly conduct electricity without any loss, without any resistance. And so it's a magical idea, one of the defining ideas in condensed matter physics, one of the most beautiful ideas certainly I've learned. And it turns out, actually, that many, many years ago, there was already a prediction that, in fact, hydrogen, the simplest of elements, which you normally think about as a gas, but if you compress hydrogen more and more and more at higher and higher pressure, well more than the center of the Earth, it turns out there was a prediction that hydrogen would first go from a gas to a metal, and then many years later, there was a prediction that that metal, upon even more pressure, would become a room temperature superconductor. Has not been realized yet, but the intuition for why hydrogen might be the best, highest temperature superconductor has to do, in essence, with its mass. The fact that it is the lightest element kind of is inversely related to how high the temperature of the superconductivity one might expect out. And so many of these materials, essentially, so the idea is that, if you physically had to compress hydrogen, pressure is force over area, you need a ton of force, and you have to pinpoint it to a very small area. Right? But the idea recently, in the last decade or so, culminating in at least this announcement, is that, in principle, you can apply mechanical pressure by pushing, or you can apply chemical pressure by literally taking a lattice of hydrogen and doping it with other elements. So, for example, very big, bulky, heavy elements like lanthanum or cerium or other things in the F element, the piece of the periodic table that we don't often think about. And so the idea is that with this chemical pressure, you can essentially make the hydrogen atoms more compressed. So it's sort of like applying pressure mechanically, but you can do so using chemistry in a much more powerful way than you maybe would be able to do with force over area. And the idea is that there has been, I think, reasonable amounts of evidence that that strategy has been slowly pushing the temperature of superconductors towards pretty high temperatures. But usually you need a combination of a ton of chemical pressure, so adding extra elements into a hydrogen lattice, as well as a ton of mechanical pressure. And what's recently been claimed in Vegas a couple days ago, Tuesday morning, was specifically that they've now been able to just use the chemical pressure to put inside the hydrogen lattice, lutetium and some amount of nitrogen, and that chemical pressure almost gets you all the way to enough pressure to be able to get a room temperature superconductor, so that you really only need to apply, it's still a lot of pressure, but not orders of magnitude less than you had to before. And so that, was the intuition for sort of what, this broad idea for this announcement was. And if it is true, it would be remarkable. I think then it would be, in some level, the closest humanity's ever been to realizing truly an ambient, under no conditions, just stable superconductor, which again, from a technological perspective, would be unbelievable.
Yeah.
Sorry. Let's, back to Felix. So please, we have a question there.
I can see it's actually a question from my friend Femi. Hi, Femi. Femi is also a very well-known author, actually. He's written a novel which has bits of real science in there. It's a fantastic book called The Upper World. Hi, Femi.
Yeah, cheers for the plug, mate. Massive congrats again on the book. I'm really pleased and proud of you, mate. 2 mini questions. So first, it sounds like your interest in physics in some ways originates from an interest in magic. I might be getting that the wrong way around, but it sounds like at least at different points that there's been that ordering of interest. So I guess my question is, how would you describe what motivates your interest in magic?
Okay.
So that's one. The second one is this idea of emergence, of like the whole being greater than the sum of its parts. Do you have a good analogy? I'm just curious, and it can be a very rough analogy, as these things always are, but do you have a good analogy for where that extra stuff comes from?
Okay, both brilliant questions, thank you. All right, on the first point, you're saying what my editor said, actually. My editor at some point said, can you explain to people like how you were drawn to physics because of your love of magic or of like fantasy writing or science fiction or something? And I had to say, actually, if I'm honest, that's not the case. I always just liked physics since I was very young. I knew I wanted to be a physicist from before I can remember, so like younger than 4. And I didn't really read much stuff about wizards and that until really I had the idea of the book. And then I started writing about it. And I had this conversation with my fiance Dominique, and I was like, they're very keen for me to draw this analogy, and I can see it would be a useful one because that'll help get new people into the subject, I think, because if they can see that they're not maybe interested in physics, but if they see that it connects to the stuff they are interested in, maybe that'll get them in, and that's exactly what I want to do. But I'm not going to lie about it. And she put it perfectly, as usual. She said, well, it's not that your love of magic got you into physics, or that your love of physics got you into magic. Neither of those are really the case. It's more that you have a kind of love of using your imagination for things, and that's the thing that drives both. So imagination is probably the main thing you need, at least as a theoretical physicist. I think as any kind of physicist, right? You need
scientists in general.
All scientists, exactly. So I think that's what you need for that. But you also need that to kind of enjoy creating these imaginary worlds when you're reading about them or when you're writing about them. In my case, but I think it's probably that love of imagination that leads both. So it's a great natural question, but actually I cheated a bit and it wasn't quite true. But so I put that in the book in the end, and Dominique was right. That was what motivated me. Okay, so good kind of analogy for this or example of emergence. What are some classic examples? I'm on the spot now. This is. I mean, the phonon's one example, obviously, but that's quite a technical one. I feel like there's some really obvious ones I can think of. Can anyone think, what's like a classic example that's used for this? Has anyone got any? Culture. Okay. Yeah, okay. I like that. Does that culture sound good? I mean, yeah, culture is not a property of any individual person, but or even institutions and things, but comes about through it. Yeah, there's another one at the back.
Maybe you could think of like an orchestra with a string section as composed of many individual players, but the sound of the section as a whole is sort of its own sound.
That's great. I suppose I should repeat it because you don't have a microphone, sorry. So that suggestion was an orchestra. So yeah, exactly. So maybe playing some huge symphony or something, it's not a property of any of the one things. And so some philosophers sort of disagree with this idea that there is a meaningful idea behind emergence. Plenty, I think, agree with it, but some would say nothing is more than the sum of the parts. And I don't necessarily disagree with that either. I'm just sort of saying that sometimes there's something that you can lose in a description by thinking of it as individual parts. So like with the rope being whipped, it's true, you could completely model that as atoms moving, and there'll be nothing wrong with that. I can model this book as a load of atoms, and it's true, it is a load of atoms, and technically nothing more, but that's kind of missing something, isn't it? I think the example I give in the book actually is an owl. So if you think of there is no elementary owl particle in the standard model, but owls exist, right? I think we're happy with owls existing. And you could describe an owl as a load of electrons and protons and neutrons, and that would be completely accurate. Though you would not be wrong to do that. But it'd also miss something, wouldn't it? Because an owl has in our culture, a cultural association with wisdom. In other cultures, they're associated with magic. Sometimes they're kind of bad spirits, sort of evil things. They have lots of associations to different people, and you'd miss all that if you said they're atoms. Mm-hmm. It's not wrong, but there's something that would be missing in the description. So maybe an owl's a good example. Thank you,
I think life in general, right? I mean, the emergence of life, right? I mean, the collection of cells, Exactly. Okay, other questions for Felix? Yep. Probably will go on for another maybe 5 minutes or so, and then afterwards, all of you are welcome to congregate with Felix and I in Cabot Science Library for some light refreshments.
All right, thank you so much for this. As I love astronomy, and as an astrophotographer, I'm really familiar with noise from a sort of antagonistic perspective. I think of it as something I associate it as being associated with uncertainty caused by randomness. But you've given me a new perspective on noise because you just discussed randomness as a compatible type of signal we can analyze because of the way in which something intrinsically random can really be constrained, like red noise being different from white noise. And I'm just left a bit disturbed now trying to understand what noise really means. I used to think of it as a limit of measurement that is due to randomness, but your example sort of transcends that. So what is your definition of noise? Is noise a limit past which we can't measure something, but something that can be very clean and well-defined?
That's a really good question. I'm going to struggle with that one a bit because I suppose we've made it difficult by picking an example where the signal is the noise, essentially. So then how would you define noise? If you typically define it in contrast to signal, then that's tricky in this case. What would you say? It's a thing described by a power spectral density, but that's not very good.
Not sure that's where we go.
No. What is noise? I don't know. That's a tricky one. Norm, I'm going to try and deflect that onto you. You got any better explanation?
See, this is what Felix does, Just kidding. Yeah, here's how I think about it. I'm not sure exactly accurate, but I don't know that there is a super clean distinction between noise and signal, but I like to think about it as there's some mean behavior of a system, okay? And on average, the system is doing something. And usually you look at that average behavior, and that's oftentimes what you're interested in measuring. What's the average number of rabbits that live in the forest? What's the average number of foxes that live in the forest? But on top of any dynamical system, there are fluctuations. And usually we are not interested in those fluctuations. We say, okay, most of the time I say, I make a simple model of predator-prey relationships in a dynamical system, and I figure out what's the equilibrium mean behavior of the number of rabbits or the number of foxes. But of course, in any real system, there are fluctuations. And oftentimes, those fluctuations sort of, conspire to make us not exactly see the average behavior. And if those fluctuations are large, they can drown out the mean in some way. And that, if we're interested in the mean behavior, and the question that we're asking, then those fluctuations hurt us. But as you say, you might be interested in asking a different question where the noise is now the signal. And what I'm trying to say is really, depending on, we're used to thinking about noise as fluctuations above a mean, and if you're interested in the mean, the noise is noise. The fluctuations are noise. But if you're interested in the fluctuations, and in particular with different constraints, let's say, the fluctuation of rabbits, may be very different depending on whether there's a proliferation of carrots around. And so, but if you're interested in the fluctuations are the signal, and that's not the noise anymore. So to me, what is noise and what is signal really depends on the angle of the question you're looking at, and it is precisely as you say, as Felix explained very well, the fact that you can learn something from about a system from the way it fluctuates. And that's something that is not super common to think about because we're so used to thinking about tracking the average behavior of a system and not worrying about learning something from the fluctuations. Does that somehow get something across? Good.
I think I can add a little more.
Please.
Oh, please do. Do you want to
please.
wait for the microphone quickly?
Do I need a mic?
Yeah,
just-
it's good for you to have a
I
mic.
think because
exactly.
they're recording the
Exactly.
audio.
I'm a retired electronics engineer, so I know a little bit about noise. I've measured. Your definition or your description was excellent. That's perfect. What is unwanted is noise, and it's just like garbage. What's not, is not needed. It's out of place. If it's in the garbage can, it's not really garbage. If it's on the floor somewhere, it's really garbage. You got to take care of it.
Right.
Now, having said that, I have seen in especially digital sound, analog to digital converters and stuff, there are three types of noise that we used to see. One is the analog to digital conversion, the zero order hold and all that. How you convert, there is some extra artifacts created. That is one type of noise. It eventually shows up in the measurements. And the second thing is called 1 over f squared, transistor noise, generated naturally by the transistors in the entire, the microchip or whatever. And the third one is the noise figures that each power converter or whatever that supplies power, that creates extra noise, its own artifacts and stuff. They all together aggregate and become the noise that is unwanted. Now, if you are looking to study what kind of noise is there, we have analyzed that. That becomes, like you said, its signal. So I think since I'm not a physicist, I can get down to real basic practical stuff. So, but of late, after retirement, I've been reading and studying and even attending classes. Professor Emeritus from Swarthmore College, I think 4 of his students were Nobel winners. He teaches in Atlanta. I'm from Atlanta. And one of the things that class I took was, this is the second question. Am I allowed to?
Yeah, go for it. Yeah,
Okay.
please.
About emergent systems, I quickly took a look at your, I think, the second 4 elements chapter. I just bought the book. And when I took that class, chaos, fractals, and something else, that is the title of that course. And it really fascinated me, concerning the behavior in sand piles and avalanches. And that thing gets extended to the extinction of dinosaurs. Basically, the idea is everything leads to criticality, and then boom, something happens. So that's where I think the whole is bigger than the parts may come in.
Right.
Now, my question to you is, you're condensed matter physicist, and you know a lot. Have you looked at, are there basic underlying formulas or principles that someone is studying very similar to, like Newton's gravitation law? And something like that, this would be at a higher level. During phase change, all of a sudden the water freezes or it becomes steam at certain temperature, and it's just uncontrolled, chaotic and spontaneous.
Okay,
Now,
yes.
would there be is anyone studying those kinds of things that regulate those phenomena?
Yeah, thank you for the question. I'd say that's the name of the game, really. Physicists really try to spot hidden connections, I think. So you try to say these two phenomena seem to be distinct, but is there something hidden that's connecting them that we hadn't seen? I'd say that's exactly what we're looking for. I think maybe the phenomenon you're referring to is what we call self-organized criticality. Is that the name for the sand piles and so on? So that's a famous example of something related to this idea of universality in physics. Which is exactly that idea, as you say. It's the idea that seemingly totally unrelated phenomena are sometimes governed by identical mathematics, and that there's a connection between those things that you wouldn't have spotted otherwise. And again, as you say, a classic example of this is like how a magnet ceases to be magnetic. When you heat it up above what's called its Curie temperature, it stops being magnetic, a ferromagnet. And it turns out there's a very deep link between that and how water turns into steam under pressure, at a certain pressure. They're identically related, in fact, with mathematics. So this is this idea of universality. And yeah, I think really it's the thing we love in condensed matter physics, spotting that two seemingly totally unrelated phenomena, magnets and water, are actually really very similar. But also it's really like the whole idea of physics, I think, is trying to spot those kind of hidden connections. Maybe I'll finish, I'll wrap things up with, you mentioned something, with the mention of noise, you said, what was it, like signal out of place or something? Was that what you said? Yes. You reminded me, and you've given me a great ending for the session, I suppose. There's a great book on Magick by a sociologist called, I think, Mary Douglas, and she defines dirt as matter out of place, which sounds very much like what you were saying. And it's the reason this is kind of important is that the original title for the book, like the working title, was The Physics of Dirt. And I do mention this Mary Douglas connection to Magick and dirt. We're going to call it The Physics of Dirt because famously, it was Pauli, wasn't it, who said it? So Wolfgang Pauli was one of the founders of quantum mechanics. And when condensed matter physics was kind of being developed, when we started moving beyond thinking about single particles to thinking about how things behave collectively, Pauli had no interest in this, and he dismissed the entire approach, the whole subject, as the physics of dirt, because he thought, well, it's just lumps of stuff, isn't it? Like, who cares about that? He wanted like the purity of just sort of single things. So we like this idea that dirt is matter out of place. Well, yeah, that's great. We love dirt. Wizards love dirt, don't they? Well, that's their classic source of doing spells. So maybe that's a good way to end things. Thank you very much for the question.
Please, everyone, you're welcome to join us to talk about the physics of dirt over in Cabot Science Library, where there are some light refreshments. Great.
How was it, Norm?
It was good. Yeah, it was great. I think it was great. It was fantastic. No, it's good.